So I wrote the software which is in the package where you can say, I'm a router. You have the highest priority, of course. Yeah, so you will become the default router. You can announce all the network prefixes you want and get all the traffic to you. It's getting better. It's getting better. Now comes the new and improved stuff. So that was the stuff from 5 years ago. Yeah, but there's way more. Yeah, you can keep the default router because the default router will send his router advertisement. There is a feature if the router power is down, he must inform everybody, hey, I'm not available anymore, so delete me from your routing entries, please. You do that by spoofing the router advertisement with a lifetime of 0. Every router advertisement has a lifetime, and so if you don't see any packets from me for the next 60 minutes, assume I'm there, afterwards delete me. Yeah? But you can spoof that router advertisement, and then the default router is gone. Oops, well, guess who they're taking now as a default router? Yeah? You can resend your own router advertisement just to be sure, and there is even a way to sending the spoofed router advertisement in a way that the default router is not seeing that. Yeah? I'm coming to that in my last slides because this is another kind of attack, which you can play there. Yeah. If you do router advertisement, systems become dual stack. And this is really the beauty in IPv4 we have today. If I send a router advertisement here on the network, every system configures itself an IPv6 address and assumes IPv6 connectivity is here. So what can I do? I can port scan on IPv6. If you're one of the guys who says, oh, I have a SUSE Linux or whatever operating system, and I don't trust that they do proper firewall filter lists, and I'm way better than they are, and you configure your own IP filter or IP tables or whatsoever filters, you might forget IPv6 because IP tables is just for IPv4. So you have to configure additional rules with IP table 6. Otherwise, you can be port scanned. All the ports which should not be accessible can be accessed. So if you have not configured filtering IPv6, you have full port access, bypassing the firewall. They will prefer IPv6. So if they do a DNS lookup and they get back IPv4 and IPv6 address for a target, they will prefer IPv6, which is wonderful. This is a very nice way to do man in the middle, even here in the conference. Hint, hint. So how about announcing a remote network as a local address? Let's say PayPal IPv6 address, and I do a router advertisement here and say, yeah, that PayPal network is local here. Have fun. Here's the web server, log in. Yeah. Ooh, warning, certificate unknown, unless you got the Commodore or whatever. Yeah. So there's lots of stuff you can do here. Yeah. And another thing, and that really surprised me. First, that I found that thing, and second, how the vendors reacted. Router advertisement flooding. Imagine I send a router advertisement announcing network A. Yeah? I know what happens. Every system configures network A on their system. So choose its own IPv6 address and so on. And now has an IPv6 address on network A. Now if there is a second router on the network who thinks, I want to have a different network announced on that network, let's say network B, sends router advertisement to everybody, all the systems configure network B, IPv6 address. So I'm as a hacker, it was really easy to come up with the idea, how about if I pretend there are 1,000 routers, pretending to have 1,000 different kind of networks, what would happen? The normal system would say 1,000 different networks on one local LAN. That's very unlikely, so I don't believe that. And that's what every good system should do. Unless you are surprised by that if you're called Cisco, for example, and you produce firewalls which get out of service in that event, or your net screen and it goes down as well, or you might be Windows, or Microsoft, yeah? And it doesn't mean any Windows version which has IPv6 active goes down. Yeah, no response from the system. 100% CPU, 100% RAM consumption. Or your FreeBSD. FreeBSD sometimes the stack even breaks, so IPv6 is gone. Yeah, the module even breaks. How can that be? I mean, this is not something like, oh, pointers overwriting and kernel something whatsoever. I mean, it's just sending some random packets and things go boom. It's really not sophisticated. Yeah? But this is what the current state of, how do you say it? I would say it's rather maturity stage IPv6 is in. That even such simple attacks work. That's why in that talk I don't even have to dig deep into stuff because it's not necessary. It's like punching a blind man. It really is. It really is. So Cisco was very responsive. They immediately said, yeah, we verified, yes, it's really a problem. Here are the fixes for all the iOS and all the ASA. So they were really fast. Who really surprised me was Microsoft. Microsoft told me, and by the way, it works if you have Norton semantic firewall or antivirus or whatsoever. It doesn't help you because router advertisement must reach your system so it can do IPv6. So they all let it pass. There is no protection against that attack besides disabling IPv6. Yeah. So what does Microsoft say to that kind of problem? It's by design, so we don't really care about that. And this was really, really surprising for me because I didn't expect that. I had lots of contacts with Microsoft in the past, and usually it was very easy to let them fix things. But here, that response was really weird. I know now that the two guys who are doing the TCP/IP stack at the moment, they just don't care. That's the reason why they're not doing anything. Yeah? And the two guys before them who were responsible for the TCP/IP stack, they care. They're kicking them at the moment that they really start fixing that bug. Yeah, even Apple got that right. Yeah, and if they get it right, then you really know it's really an easy task. So how to do this attack? I mean, it must be highly sophisticated, so that Microsoft doesn't want to fix that. It's this command. Yeah, flat router, your interface, and then it's doing this stuff. It's really that easy. So if you would do that on the conference, all the Windows systems might not work anymore. So you should better not do that. Hint, hint. Good thing the toolkit is not optimized for wireless LAN, so you somehow save here. Another topic, IPv6, we have /64 subnet mask. And this is default, this is standard, and it must be that way. If a subnet is that size, how would you do in a live scan? I mean, scan 4 billion multiplied by 4 billion machines and wait until your grandsons can see what the results of your scan are of just that one network? It doesn't work. Well, at least many women, many children, okay. But anyway, so it doesn't really work. So what was commonly said is that remote and live scans, so the ping scans as we know them, don't work in IPv6. Well, one of the jerks was me in 2005. But then I put some brains into that last summer, and thought about how it is possible to identify remote systems. Well, we can't scan the whole range, of course. 4 billion by 4 billion is way too large of a number, even if we say we have terabit networks or whatsoever. Yeah? Doesn't scale enough. There are no broadcasts anymore, and we can't use multicasts unless we're local anyway, and then it's easy. We can use search engine in databases, but this only helps us so much. I mean, who puts their whole network in a database that these people access that? Not so likely, but some will be, like the web server, or you might find the mail server, so at least a few entry points will be there. You might find stuff in the DNS actually, because IPv6 addresses are long. So you don't want to write them down every time. So you will put them into the DNS. And people might use common addresses for configuring. That was the theory, which I tried to check if this is really the case. And I thought if I combine these three, I should find at least some hosts. And I had no clue what the percentage of average number of hosts found would be, if I would find 10% or 50% or whatsoever. And that's why I made some statistics. Prior statistics, I told my ISP, yeah, there might be some complaints because from my server all we do statistic analysis on the IPv6 internet to see what the distribution is and check every month how much more systems there are now and then present at the conference. They said, yeah, statistics and tests, wonderful, yeah, no problem at all. If there's any complaints, we tell you, no problem at all. Yeah, since then I'm scanning monthly the whole IPv6 internet. And they're fine with that, which is very nice. Now, I think since 2 months, they actually know what I've been doing, which is not so much statistics on that stuff, but on the attack type, but still they're fine with that. Yeah, there's a big black or several black spots in my technique I'm doing here. I'm focusing on server networks. Yeah? There's lots of IPv6, which is, let's say, on the DSL side, the consumer side. I didn't look at that. Yeah? So what this technique I'm doing here is focusing on server networks, yeah? Like in a DMZ or something. So first, search engines. I looked for all the IPv6 search engines there are out there and dumped all the directories. For some, this needs some tampering with the HTML parameters to get post parameters so I can easily dump the whole database. But it was not very hard. And I found 17,000 possible domains and subdomains. Why? Because first I wanted to scan all the DNS. So I generated a big list with 3,200 possible host names. So word lists, then standard DNS hostname brute forcing list, some IPv6 special stuff, and put them all in a big list. It was over 3,200 host names. Then I started scanning all these 17,000 domains. Yeah, I didn't find that many. I mean, if you compare, it's not that much. But only 2,000 unique host names were in there. So 1,200 were never used from that list. I thought, okay, that's a bumpy start. That's not really much. I thought the IPv6 internet would have way more than that. Okay, but now I analyze the DNS results. There were 15,600 unique IPv6 addresses on 7,300 networks and 5,800 unique host addresses. And now this is the point where it's interesting, because the networks, okay, networks, but the host part of the address, this is what is interesting. And the host part is if you have an IPv4 address, 192.168.0. That's the network part, and the last number, if it's a sys class, is the host part. So that's what we're interested in, the host part. And I did an analysis on that. And what I saw in the statistic is, well, there are a few host numbers which are used very, very commonly, and the rest is then just once. So they are unique. But this part, if I just scan for these, I will statistically find them very often. Okay, so I did a real analysis of these numbers I found. Some came from auto configuration, some were configured by hand, some were by DHCP. Auto configuration can be done by MAC address, which is the default, unless on Windows. On Windows, the privacy option is enabled by default. Privacy means it generates its own IPv6 host part of the address every day. So every day it has a new IPv6 address. It can be done by hand, and this was either a pattern like : 1, : 2, : 3, yeah, so easy stuff, or it was really looking random. So then it was of course tough. And DHCP, all the DHCP implementations